Okay, are you ready for some more hard code coding stuff? Yeah, okay. So we have a CEO in the house. Vassil is the CEO of Homeheed, and he's going to talk about a little image recognition and some interesting stuff around there. So please, you're welcome.
Thank you very much. So yeah, I'm Vassil, and what I'm going to tell you is the hardcore technology of Homeheed, the company that I work for. Just a bit about myself. I used to work at SoundCloud. That was a pretty good company and still is a pretty good company. I was doing some deep things in there, like trying to find the genre of a sound based only on the MP3 file without any text data or anything. Then I worked at Lindblom, where I was like kind of the Joseph from the previous talk, which was like one of the first guys trying to do everything manually as much as possible and stuff like that. Now I'm working for a company called Homeheed that is doing something. It's a very small company. We're still a startup, and we're doing some interesting stuff in the real estate. That's why you'll probably see some pictures from apartments or something like that. Okay, let's start with the problem. What I'm going to talk about. We at Homeheed have 7 million images, and the images look like this. And that's not the problem. Like, that's a pretty fine image. The problem is that in that database of 7 million images, we also have images like this. Yeah, so do these two images look similar? Of course, that's because they have the same apartment, they have the same home. But even though the content is the same, they are not exactly the same. First of all, let me see if I have a mouse. First of all, this is obviously some kind of edited or something like photoshopped, because it has something that is completely artificial. So not exactly the same, because one of them was photoshopped. Also, this one is transformed. You see, this is like rotated and a little skewed, so kind of transformed. Also, check this red plastic thing. It's over here on this photo, missing over here. So obviously, these two images were taken at different time. It's not the same image, just edited. It's two completely different images taken from probably two different cameras, probably from two different people. And our goal is to be able to say these two images are equal. That's our goal. We need to be able to say the content on them is the same. Why? Because we need to okay, I have a specific demo at the end which tells exactly why, but let's let's say that we need that. So, what's the talk going to be about? The talk is going to be about how we implement this equality relationship. How can we do that? How can we compare images based on their content without knowing that they are the same image edited or something like that? And the second part of the question is, given an image, how can we find all equal images in our database? The presentation is going to be based on the first question. The second question is probably a topic of another presentation. I won't be able to cover both of them. But the answer of the first question, how can we implement this, needs to be scalable to scale to the second question. That's why I'm going to present a solution that is scalable for the second question. Now, image fingerprinting is in the title of the topic. So I'm going to give you a very, very brief overview of what fingerprinting and specifically image fingerprinting is. First, given an image, we need to convert it to another representation, extract something from it, and pretty much do some, like, given a file of an image, make another file that is different. This file, we convert all images to 17 kilobyte files. That's the representation. And the important thing about that representation is that it needs to be descriptive enough. By descriptive enough, I mean I can tell if two images are equal using only their 17 kilobytes representation, without having the images at all. And if you can do that, the 17 kilobytes file is the fingerprint of the image. It's like a good enough representation of the image, so we don't need the image, just the fingerprint. That's where the name comes from, like person fingerprints are good enough to identify who you are. The same thing visually, just to be a little bit more simple. We have an image, we convert it to a fingerprint that's 17 kilobytes. We have another image, we convert it to a fingerprint that's 17 kilobytes. Then we need to be able to do the relationship, the equality relationship, based only on the fingerprints without having the images. That's our goal. That's what we need to do today. And how exactly is a fingerprint extracted? That's the first question. The second question is, if we have the fingerprints, how can we implement the matching? Well, that's what I'm going to tell and present until the rest of the presentation, but let's first do a quick demo. If we can do that, this is what it should look like. Oops, sorry, not that one. Where is my mouse? So, not that one. Okay, so yeah, we have two images here. The 10 level image that is static and the dynamic image from my video stream. What we're currently doing is we have fingerprinted the first image, taken the fingerprint, and now we're fingerprinting every frame from the video stream and trying to match the left image to the right image. Currently the green lines are something like I'm trying, but they don't really match. But what would happen if we actually put 10 level in the second image? Let's see. So, that's a match. The blue lines are actually saying I can find the left image here in the right image, and the blue lines say exactly where. And this technique is kind of robust against rotation, against translation, of course, like moving it, robust against scaling, even against skewing. I would say even against removing some part of the image, but that's pretty hard. Let's see if that can work. Yeah, it says I can find the left image in here and it should continue over there. I'm not exactly seeing it. The green lights are saying I'm seeing this, but it should be over there. Okay, so that's our goal. How can we actually do that? Let me. There. Okay. There are two big parts. The first one I just mentioned them. The first one is extraction. The second one is matching. The first one is converting an image to a fingerprint. The second part is comparing to fingerprints. The extraction also is split into two parts. Detection, like if you have an image, the first part is detect what is important in that image. We call the important points key points, and I'm going to talk a lot about them. And we extract exactly 500 key points from each image. Then the second part is description. Each of these key points needs to be described in some computer readable way. We describe each key point with 32 bytes or 256 bits for each key point. That's the first part. I'm going to show you how exactly we're doing it. The second part is matching. So we have two fingerprints of two different images, and we want to know, are they different, like by our relationship of content different or content is equal? And the first part is matching key points. We do that with Hamming distance and thresholding. And the second part is matching the whole image. We do that with ransack and homography. Now, this is the agenda for the rest of the talk. I'm first going to go to detection, then description. After we have the fingerprints, I'm going to go to matching key points and then matching the whole image. Starting with detection, how detection works. how to detect key points. First of all, let's start with the left image. Like most of the presentation is going to be based around the left image, the 10 level. It's an interesting image, but for computers, they need a little bit more specific things. And the most interesting parts of that image are the so-called edges. Edge is where contrast between two pixels in the original image is high. For example, we have a black line over here and a white pixel right next to it. That's a very high contrast spot. And this creates, of course, an edge over here. That white edge means that there is a high contrast between neighboring pixels over here. So we convert the original image into edges. By the way, most of the things that I'm going to show and explain are pretty standard. OpenCV, Open Computer Vision, is a library that we use mostly, and most of the things that we do are pretty standard in there. So that's not something that we have implemented, we're just merging things up. So that's the first part of detection. We need to detect edges. Second, edges are fine. They're much more simple than the original image, but still they're kind of too much. We need 500 key points. What is an interesting point over here based on the edges? Well, again, similar to the first idea of the edges, where neighboring pixels are interesting. Like over here, it's pretty like straight line. But look right over here, right at the tip. It's sharp. Two edges that connect into a sharp node. That's actually very interesting, and that's how we find key points. That's choosing key points. We need to choose the 500 most interesting key points, and we choose them mostly by how sharp they are, how different they are than the rest of the key points, than their neighbors. And for example, over here, around the sharp edge, we have multiple key points because that's a pretty interesting point. Now we find 500 interesting key points based on that idea, that the more sharp the edge is, the more interesting. Next, we need a little bit more of the key point. We know its location, but we also need its size. Like, for example, this key point over here is interesting in that region. In a smaller region, it's probably not that interesting. In a bigger region, it's not that interesting. But in that specific region, in that size, it's very interesting. Whereas this key point is very interesting in both very high and smaller regions. I'm not sure how good, yeah, probably here is better. So we need the size as well. Each key point has a size as well as position. Then we need the rotation or the orientation of the image, of the key point. Because we need to be invariant to, resilient to rotation. We need to be able to rotate the 10 lever and still get the match. In order to do that, we're pretty much asking where is the edge pointing to, where is the sharpness of the edge pointing to. So these two lines are going like that and then like that. So the edge is going over here. And we're asking that for every single point. This one lever is pointing at that direction. Why do we need that? Well, that's the first thing that we're going to use in the next part, which is how do we describe key points. Now that we have 500 points, we know their size and their orientation, how can we describe them into bits, into something useful for a computer? First, we rotate them. That's why we need the orientation. We would rotate them so that the orientation is perpendicular to the axis. We're going to do that for every key point everywhere, whenever we extract a key point. So the original image was like that. The orientation was over like that. We rotated it like here, perpendicular to the axis. If we get 10 level, put it on the screen and rotate it over here, that should look, the orientation would look something like that. But since we again would rotate it perpendicular to the axis, we will make it exactly the same, as if they were not rotated ever. That's the idea of the rotation and the rotation. It's pretty much rotation resilience. Then part 2 is picking random pixels. That's a little bit harder to explain how it works, but there is a pretty good research about it, like not exactly why, but more like, does it actually work? Yes, it works. So just picking 2 random pixels out of the region that is interesting, and then just comparing their brightness. Like, is one of the 2 pixels brighter than the other? If the left pixel is brighter than the other, then return 1. If not, return 2. That's the simplest thing possible. That's one small feature that's describing this key point. It's pretty much saying just that that white pixel is brighter or not brighter than the red pixel, and we know the exact location of those pixels. It's not much of an information, but if we repeat that 256 times with 256 random pairs, that's now a relatively good representation of the key point, of the region around the key point. And these 256 bits, because every pixel pair returns a 0 or 1, returns a bit. These 256 bits is our description of the key point. That's just it. Nothing special. That's the brief description. I mentioned it in the previous slide. Brief descript. It works like that. Just random pairs. Okay. Now what? We have 256 random pairs. What about the whole fingerprint? How can we represent the whole fingerprint? Because with 256 bits, we represented just one key point. For the whole fingerprint, we have 500 key points. So we just get the descriptions of all of them, plus their locations. We need to know where exactly in the image they are. We don't need size, we don't need rotation or anything else, we just need their location and their description. After that in total is 17 kilobytes if you compute it. 500 multiplied by 32 bytes, plus 500 multiplied by 2 bytes. That's our fingerprint. Pretty simple, huh? Just 500 key points described with their locations. That's our fingerprint. And how can we use that to actually match? If we have 2 fingerprints, how can we say if these 2 images are equal or not? Let's start with just the smaller part, just key points. If we have 2 key points, one from the one image, another key point from another image, what happens there? Let's say that this is one of the key points, 256 bits. Sorry. Another key point that's again described the same way. What's interesting about these bits is that they come from random pairs, but the random pair in one description is the same as the random pair in another description. In other words, if you have 2 key points, when we say random pair number 2, it's at exact positions. The pixels are at exactly the same positions in both of the images, in both of the key points. So if this 0 and this bit and this bit are equal, then the 2 pixels at that positions in both of the key points have the same relative brightness. So how we compare key points? We just do an XOR. We compare, XOR is pretty much saying equal bits result to 0, different bits result to 1. For example, 1 and 1 results to 0, and here the third one, 0 and 1 results to 1. That's classic bit operation, XOR. This one, the pop count of the result tells us how many different bits we have in the description. Right here we have 2 different bits. That's the Hamming distance. That's pretty much the definition of a Hamming distance. And then we do something pretty simple and straightforward. We just use a constant threshold that we have to think out of, say 3. Anything that has a Hamming distance of less than 3, we say that it's a match. This one has a Hamming distance of 2. It's less than 3, so we say, okay, these 2 key points are match. They're equal. In an image, what that means? Well, if this is one of the key points, and this is the other key point, if we find a match, we draw a green line, which means we have found a key point on the left image and a key point on the right image that are equal. I think that these 2 key points are equal. Okay, but that is how we match key points, but that doesn't say anything about images, like the boolean, how that works. How we match 2 images. That's a bit more involved. What we have, first, what do we mean by match? We mean that we can find a homography from the left image to the right image. What is a homography? It is a linear algebra transformation from the left. For every pixel in the left image, we can say which pixel in the right image represents that pixel. That's pretty much that. So we can say that this rectangle is represented by this kind of skewed rectangle. And for example, the edges, this point, is represented by this point in the right image. That's what we mean by match. A homography from the left image to the right image. So that we can say each pixel in the left image is represented by that pixel in the right image. How can we find a match? How can we find a homography? First, do you know how a homography works, how it works? It's a classic linear algebra thing, and so it looks like a matrix. Nothing special about it. The most interesting thing about homography is that it's uniquely identified by four pairs. If you give a pretty simple algorithm, 2 images and 4 specific pairs, you can find one specific and unique homography between those two images. So here is how we can try to find the homography between these 2 images. Given those key point matches, we already have matched all key points that we have, and we have found these 8 key point matches. First, just to let you know, this is how our algorithm looks at our image. It has only the fingerprint, and the fingerprint tells the fingerprint knows how big is the image, so that's the borders, and we know the matches. But our algorithm doesn't see the image anymore. It uses only the fingerprints. So that's how we need to find a homography based on this data. How we do that? Well, we're going to do random sampling. Let's first just pick any 4 pairs, because we know that 4 pairs can uniquely identify a homography. Let's pick any 4 key point matches. For example, these 4. Then let's create or find the unique homography that covers these 4 pairs. So this rectangle would be transformed to this rectangle based on these points. Does that look okay to you? Is that a good homography? Probably not. Probably not. But our algorithm doesn't know because he can't see the images. He needs to find that without looking at the images. He needs to know if this is a good homography or not without looking at the images. So what it does, it tries converting every single point in the left to a point in the right based on that homography. And checks if the correct point is close to what is converted from using the homography or not. And then it asks, do the majority of points look okay? Do the majority of the points are converted from the homography correctly? Blue lines are correct conversion, red lines are wrong conversion. So no. Here, it's not a correct conversion because at least not most of the points are correct. Okay, let's try again. Let's repeat and choose another 4 random matches. Let's use these 4 right now. Do the same, get the homography. How about that? Looks better, right? Okay, let's see what would happen with our test. Let's test each match, each key point match based on that homography. The result is like that. So we actually know which key point matches are correct and which are wrong. We cannot have only correct matches. The algorithm is approximate, so like 50% of the key point matches should be okay. Even more, like 60-70% of the key point match should be okay. But we always have outliers, the red lines. Matches that we don't really know why they match, but they match. Hopefully, if they are small enough, Ransack can find the correct homography pretty quickly with this random sampling. Just random picking 4 matches and checking the homography based on that. And so, yes, this is the homography, this is the key point match, and that's how we matched the images. Those 2 images I recall because we were able to find the correct homography between those two. And now, a very interesting, at least to me, question. Why the fuck do we need this? At least us. But why? Well, I would like to show you another demo. This is a bit more specific to our domain, but it explains pretty well why we need such a thing. This is an apartment listing. Pretty simple apartment listing in the center of Sofia in Wozenets. It works fine. It was posted on 29th of January. Okay, fine. Let's see the history of this image. What happens on the next day, on the very next day, on 31st of January, on 1st of February? Oh, something interesting happens. Another listing of the same apartment pops up. So we have this one with the original listing, and we have another listing from somewhere else. Somebody else posted the same listing. Are they equal? Pretty much yes. They're saying the same numbers as price, same size, and so on. And most important of all, the images look the same. Probably in a different order. What happens next? One more day, one more listing is added. And it's even cheaper, while the original one says that much. So I'm not going to go into the details of the domain, but this is quite normal, and this actually is a why. It actually costs that much. Okay, several more days, one more listing. Okay, this one looks different, right? Does it? What's happening here? One more day, one more listing. Several more days, and again one more listing. And this one is cheaper, bigger, and it's in a different neighborhood. And by the way, yeah, it's still the same. This is quite normal in our domain. And it's very hard to find things like that without actually using the image, without using the matching that I just explained. Okay, so what happens next? That's a very interesting story, at least to me. First of all, most of the listings disappear. This very specific day, 17th of February, most of the listings disappear. That's a very strong signal in our domain. We know that that's a very strong signal that the apartment was just rented out. It's no more it's not on the market anymore. You can't rent it. Then why the hell are these two still on the website? I can tell you, you probably know. Hey, can I see that apartment? Oh, that one was just rented out, but I can show you something else. And how long do you think these listings stay on the site? Like the apartment was rented for 16 days, and these stay from January, February to, let's say that it stops here, to July, 5 months. And we need to know which apartments, which listings are actually real, and which are outdated, fake, or any other else. And that's why we really need something that can match images. And why images? Can we just use the description, like a size, price, and so on? It's a good start, but see what happens. After the apartment is rented out, another listing appears. And check the price. It's 33% less. It's instead of 1,500, it's just 1,000, even less than 1,000. And it's in a completely different neighborhood, like it just crossed half of Sofia. Now, without images, we can't find that. There is no way, based just on the textual representation, that we can tell that this listing over here is the same as this one without looking at the images. There is just no way. They're so much different based on this description. But it gets even worse. Several months afterwards, somebody else posted something like that. Like even cheaper, even further away. And my personal favorite is definitely this one. It's like a third of the price. It's 2-room now, but it's bigger. The original is 3-room, 100 square meters. This one is bigger, but 2-room. And I don't know if you can see here, it says how many images you have. The original one has 12 images, this one has 7 images. Why? Because you can convert a 3-room apartment into a 2-room apartment by just removing the images of the third room. Yeah. And that's it. I'm a bit too early, but I hope that we will have time for questions.
Great. So we have 8 minutes for questions. Who's first? Okay.
Actually, I use Homeheed when I was searching for apartment.
Thank you.
And actually, I'm interested if there are some failures of this algorithm, and if you can show some of these failures, like
Some fails or what?
failures. Does it works every time? Maybe some strange pictures that actually were matched, even though that they are really different.
Yeah, I can show you, but I don't really have them right now. I have to search through my library. We can discuss that after the presentation. We have some interesting pictures that are matching, and we don't know why. But actually, we have some that we don't know why, but we have a lot that we know why. Most of the pictures that don't match actually are because they are too generic. Imagine a picture of Vitusha and another picture of Vitusha from like 10 kilometers away. Completely different apartment, pretty much the same view, but not exactly the same. They match, and we somehow think that these two apartments are similar because the images of Vitusha match. And that's why we have a specific algorithm that tries to check how unique is the image, how representative, how much information it has. Because that's pretty common, like matching very low information images together.
And I have another one. When we have the key point and we get the range.
Yeah, the size of the key point.
Yeah, then we start getting some two random points to get 0 or 1, right?
Yeah.
So when we have, let's say we have two pictures and we have the same key point that we are looking, but isn't it a problem that the order of the bits can vary a lot on the random pick that we've made?
Yeah, so what we do is before starting to describe even, we say the first bit would be represented by the pixel 30% from the top to bottom and 25% from the left to right, and the pixel 90% from top to bottom and 90% from left to right. And we say that the first pixel will be represented by these pixel pairs, the first bit. And we always use the same positions for all key points. So
it's not random.
Sorry?
So it's not that random.
It's not that random. The random pick is before we start describing them. Once we choose random 256 pairs, they are always at the same position, and they are always at the same order. Is that the answer? Does that answer your question?
Yeah. And final one, sorry. How we choose the range? How big is the range?
Like the size of the key point?
The range.
The radius of the key point. Yeah. It's based on how interesting is this part of the edge, how interesting is this part of the edge, and how interesting is this part of the edge. The more interesting, the more important is that key point. We're actually looking at many, many key points, like, for example, 10,000 key points, and getting the 500 most interesting of them. And the range is chosen mostly. First of all, this is something that our algorithm does in computer vision, so we are not specifically choosing the range manually, but the range is chosen by, let me try to go back to that part. Sorry. Yeah. So this one over here, just that, would probably not be that interesting because it's pretty much just white. This one is interesting because it has an edge, and it also has many other interesting curves on the edge. It pretty much computes the variability and the uniqueness of that part. How similar it is to, let's say, that part, which is pretty like just black, not interesting at all, compared to that one. That's pretty much the general idea. The more uniqueness in the region, the more interesting, compared to the size, like, yeah.
Okay, last question.
Hi. So how do you control, so between two images, if the light is very, very different? So for example, in the original image, the room was very bright,
Yeah.
and the other image, the matching supposed to be matched,
Yeah,
it's very dark.
I understood your question. Here is the answer.
The contrast, yeah, how do you control that?
The bits are computed by comparing the brightness of two pixels in the same image. So if one image is much brighter than the other, then both of the pixels would be much brighter, and we are comparing the difference between them, not the general brightness of the image.
Okay, I don't think we have time for more questions. One more time, huge round of applause for Vasco. Thank you.
Thank you.